Hello, once again, AP Calculus AB students, Mr. Record here. We are now going to take a look at my second example in the curve sketching series. This would be out of section 3.6 of Larson's 9th edition. Example 2, part B. Perhaps you had a chance to take a look at my example 2, part A, which was the sketch of a traditional rational function. In this particular example, we're going to tackle a little bit more complex kind of function. I guess I could call this some kind of a rational trigonometric expression, cosine of x over 1 plus sine of x. And we're going to go through all of the analysis that we did in the previous problem in determining a very accurate graph of this particular guy. And that does involve going through the typical 9 pieces of information that we see right here. Some of them are calculus-based, some of them are algebra-based or trig-based in this case. So without further ado, we will push on and we'll return to this page here once we get to our information, and then will allow us to graph. So our first item to discover is the x and y intercepts of this graph, and we're not going to really do anything any differently than we did before. To find these, we would go about the same procedures as last time. So to find the let's say the y-intercepts initially, we know that y-intercepts occur whenever the values of x are 0. So if we can find the value of f of 0, we have pretty much have this taken care of. So the cosine of 0, all divided by 1 plus the sine of 0, would be, well, the cosine of 0, we of course know that to be 1. And 1 plus sine of 0, the sine of 0 is going to be 0, of course. So 1 over 1 plus 0. Not so sure what's going on with the marker here, but we end up getting 1 as the y-intercept. Now, we could certainly write this ordered pair as 0, 1, and we'll kind of circle that for future reference. And then we're going to move on to the x-intercept at this stage. Finding the x-intercept is just really a matter of taking your function, f of x in this case, and setting it equal to 0. And as we've discussed many times, students in my class, that if you have a rational expression, a fraction expression that must be set equal to 0, then all you've really got to worry about is when the numerator is equal to 0. So when does cosine of x equal to 0? Well, it turns out that cosine of x equals 0 many, many times. Lots of different ways that you guys could go about finding this. One of my favorite ways is just to think about what the sketch of the cosine curve looks like through a few cycles. Looks something like this. And we find out, well, what are these particular x value positions where the graph does indeed cross the x-axis? And so upon looking at this a little bit further, we find that, this first position right here would be the value of x being pi over 2. And then we have another one happening over here at 3 pi over 2. And then for that matter, we could argue that these particular values over here left of the origin would also be potential x-intercepts. And that is true. And it really doesn't stop there. We could say plus or minus pi over 2, plus or minus 3 pi over 2. But this graph is going to go on and on and on because it is a periodic function. And you've got to get to a point where you say, hey, I'm only going to worry about so many of these. And if we were to go back and look at the coordinate plane that's been laid out for us, we notice that it only goes from a negative 2 pi to a positive 2 pi. So we can stay within those boundaries and I think be pretty safe. So we're going to return back here and then just declare the fact that we really only have 4 x-intercepts. Plus or minus pi over 2 comma 0, plus or minus 3 pi over 2, 0. Now, before we go on, I need to make sure that we are all aware of something. Yes, it does seem as if there are 4 different values for which this numerator was going to be equal to 0. But we must be very careful to understand that if the denominator were equal to 0 at that same position, we would not necessarily have an x-intercept. So what I'm going to do is just hold off on encircling either of these 4 points and wait until we do some of our further analysis to truly determine when we have an x-intercept and when we don't. That should make a little bit more sense as we get to that particular part. Okay, for part B, any symmetry. Symmetry seems to be the problem that students have the most trouble with. And it is an optional type of analysis, in my opinion, because if you do all of the other analyses correctly, the symmetry typically will take care of itself. But I would like to kind of briefly talk through this because it is a good, important fact to have mastered. Talking about y-axis symmetry in this case, what we've got going on is, well, a couple of different things. For the y-axis symmetry, we're going to be able to do a quick analysis here. So if we remember, y-axis symmetry is built upon the premise that your function, f of x, would undergo this particular property. F of negative x would essentially change very little. It would be the same as the original function, f of x. And I notice I have my little summary of symmetry over here off to the side in case you've forgotten. So what does that say about this guy? Well, if we were to replace all of the x's with negative x, we would end up with the cosine of negative x in the numerator, all divided by 1 plus sine of negative x in the denominator. Now, it becomes important for students to have a pretty good handle of a couple of geometric properties, and that is the fact that the cosine of negative x is indeed equal to the cosine of positive x. In other words, cosine of x in itself is this even function. Cosine, you'll notice, if you remember my graph up here, does have this nice symmetry about the y-axis. But we also have to keep in mind there is a denominator going on in this problem, the 1 plus sine of x, which in this case, when we replace x with negative x, we end up with a very interesting result, and that is that the cosine of negative x is negative sine of positive x. Now I can illustrate that probably best by picturing the sine curve here. And it's basically saying, for a quick recap of the trigonometry, is if you've got a certain x, let's say it's right here, and we have a y value of some sort at that position. Well, if we were to take this same distance, x, over to the left of the y-axis, which would put us, right about there, say, we'll notice that we have a y value down here with a completely different sign. This y-coordinate would certainly have the same magnitude as this y-coordinate, but yet with a different sign, hence why we say negative sine of x. And I completely understand that this function can be completely written as cosine of x over 1 minus sine of x. And what we discover there is that this does not show the y-axis symmetry whatsoever. In other words, we don't have the same exact function that we started with, which was cosine of x on top and 1 plus sine of x on bottom. And you can also discount any potential origin symmetry as well, because with the origin symmetry, as you can see over here to the side, replacing the x with negative x in the function should yield the same exact function with an opposite sign overall, and we have neither achieved that. So we have pretty much come to the conclusion that there is no type of symmetry whatsoever. No y-axis symmetry, nor origin symmetry. And while it might seem, oh man, we just wasted our time, I don't think so. I think that's going to be a nice little fact that we can file away once we get to the point where we've begun to graph. Okay, moving on, we get to part 3, talks about finding the domain of the function. I, again, typically call this an optional type of topic because of the fact that discontinuities in part 4 are typically going to take care of this, and there's also a nice sort of relationship even with part 5. But if you get down to the nuts and bolts of it, your discontinuities and your domain are going to go hand in hand here, because you notice with this rational function, you have a denominator of 1 plus sine of x that we simply can't have a 0 in that spot. We cannot have 1 plus the sine of x being 0. So we have to think to ourselves, well, when does that happen? When does 1 plus sine of x equal 0? Well, that occurs when, of course, the sine of x is negative 1. And again, there's a variety of ways that students can figure this out, one of which certainly is using the unit circle. Another interesting way is to think about, once again, the graph of the sine curve. And I'll just take this from negative 2 pi to positive 2 pi, and we say to ourselves, at what point do we have a y value equal to negative 1? Well, certainly here and certainly here, that seems to happen. And we find out that these x values are pretty easily determined as negative pi over 2 and positive 3 pi over 2, which should ring a bell. Not only have we found these two particular values that actually will go a very long way in determining the answers to 3, 4, and 5, we've actually been able to determine that 2 of our x-intercepts, or what we thought were x-intercepts, are in fact not x-intercepts at all. So I would like to take care of that first if I could. So I'm going to go back to our previous screen, and you remember whenever we had performed this particular calculation, we had said that originally plus or minus pi over 2 comma 0 was one of our x-intercepts. Well, I think we can safely remove the negative. And for that matter, I can go ahead and get rid of the plus altogether. And then we notice that the positive 3 pi over 2 should not any longer be a position where we had an x-intercept. So we can now officially declare, if I can get to my pen here to work, these 2 points, and only these 2 points, are indeed going to be serving as our x-intercepts. That would be negative 3 pi over 2 and positive pi over 2. Okay, now we'll move forward. Notice the domain of the function. Well, it seems like we're going to be pretty safe with practically any other value of x besides the values negative pi over 2 and 3 pi over 2, as long as we're staying on that original negative 2 pi to 2 pi domain. Now that's kind of funny here. So I might want to kind of preface my domains by saying on the interval negative 2 pi to 2 pi, we can say that our domain would be everything from negative 2 pi up to negative pi over 2, union with negative pi over 2 up to positive 3 pi over 2, union everything from 3 pi over 2 up to and including 2 pi. And again, I don't make a big deal out of whether or not students put parentheses or brackets around these end results here. It's pretty immaterial to me because we're going to be able to sketch the graph regardless, and we know that that's where it's going to start and where it's going to end. But all truth be told, the function is actually defined at negative 2 pi and 2 pi. So the discontinuities, I don't think you got to do much more. Right? You've already done the work. You've put the work into that, so you can go ahead and say the discontinuities would be here, negative pi over 2 and positive 3 pi over 2. And again, I might want to preface that or at least state after the fact that only applies on the interval negative 2 pi to 2 pi. And then if we want to figure out, well, what are the equations of vertical asymptotes? Well, once again, equations of vertical asymptotes are found whenever a denominator can be set equal to 0 post any type of cancellations. Obviously, nothing in this function here is going to cancel initially. So we can say that the vertical line x equal negative pi over 2 and x equal positive 3 pi over 2 are going to serve as our vertical asymptotes. Now with the horizontal asymptote, this can be a little tricky. I have a lot of students sometimes that in an analysis of a problem such as this, they tend to hold off on the horizontal asymptote and think, well, let's just put everything else together and then see what happens towards the end. But just to give you a heads up here, really with the horizontal asymptote idea, Once again, you're just looking at where the limit of the function as x approaches positive infinity and then negative infinity would exist. And finding the limit of this must be done in a sort of intuitive fashion. And students that are in my class, we've done quite a few of these. I'm hoping that you have some recollection of the fact that if we do try to let this x become infinity or get very close to infinity, the cosine of infinity doesn't really have a specific value, but we do know that it is some constant that lies between -1 and +1. So for all intents and purposes, we have a constant. Well, if we were to divide that by what would happen when we have 1 plus the sine of infinity, it's really something very, very similar. The sine of infinity is, again, some constant between -1 and 1. And if I were to add 1 to that, that really would just give me some constant. I'm going to use the letter k because it doesn't necessarily have to be the same constant as the numerator. But this time it would be a constant that lies between, well, in this case, between -1 and 1, but we must add 1 to both of those, so that would be between 0 and 2. And it turns out that you really don't have any handle on what the behavior is of the entire function as x approaches infinity in both the numerator and the denominator portion. The same thing applies when x is going to approach negative infinity. You know, we've got just too erratic a behavior. What we have here is a function that I don't want to say that it necessarily oscillates, but it doesn't have, or it does not demonstrate behavior very conducive to a horizontal asymptote. And we're going to find out as well that the oblique asymptote idea is sort of out of the picture here. Very rarely, if ever, would I say a trigonometric rational expression would have an oblique asymptote because of the long division that produces a first power polynomial quotient just isn't going to be relevant. Okay, so we've got through our domain, discontinuities, and asymptotes. I'm going to circle these because these are good to go. We're going to move on to the next part, which is where the calculus finally enters the picture. So we're going to take care of our first derivative test. So we're going to take f prime into consideration. We're going to have to use the quotient rule. I'm going to move through this pretty quickly, so if you need to pause the video, feel free to do so. But the derivative of the top multiplied by the bottom minus the numerator now multiplied by the derivative of the denominator. And then it would be placed all over the denominator squared. Our next task is to then simplify as best as we can here. And I will distribute my negative sine of x. And I'll multiply my pair of cosines. Then we look and say, is there any more simplifying that we can probably do? And then the answer to that is yes. We can factor out a negative out of the numerator because that's going to set up a very interesting identity. Perhaps you guys see that coming already. And that particular identity happens to be the fact that these two guys right here will all equal 1. So we'd have the sine of x plus 1 with a negative in front of it, of course, in our numerator. It's not a big deal, hopefully to all, if I say 1 plus sine of x. Over, of course, 1 plus sine of x quantity squared. And finally, we can do a little bit of cancellation and come up with the most simplified result of our first derivative. Negative 1 over 1 plus sine of x. So at this point, we have something that we can then use to find some critical numbers for. And the definition of critical numbers, if you recall, would be when our derivative is set equal to 0, which in this particular case, unusually, is never going to happen because the numerator is a constant -1, therefore you can never have 0 as a result. But the second case, when the derivative is undefined, will be applicable here. And you might look at this and think, this sounds a little bit familiar. Have I seen something like this before? Well, of course we have. This is exactly the same equation that we were solving when we were finding discontinuities, ultimately the positions of the vertical asymptotes. So it makes sense that places where the derivative would be undefined would certainly be places where we have the vertical asymptotes. So if you recall, I'm not going to do that work over again, but if you recall, those two positions happen to be at x equals -pi/2 and positive 3pi/2. All right, so we have our two critical numbers now. Now we're ready to set up our chart. I need to make sure that I keep my derivative visible here on the screen, and we'll go ahead and set up our little lines here for my chart. And let's see, let's move this guy down a little bit. That would be the test line. And seeing as how I had two critical numbers, that would equate to 3 different intervals here. Let's see if we can make these lines a little straighter. All right, I think we're all set. If you've seen any of my videos before, you know that I like to label the rows with the following headings: interval, test, sign, and conclusion. And in this particular case, my intervals would start with -2pi. Remember, that's exactly the size of the, or exactly the location of the left boundary of the graph that we were provided. We're going to take that to the first critical number and just keep going where we left off. You might be a little cautious in selecting some appropriate test values here. Let's make our life as easy as possible. So on the interval -2pi to -pi/2, it seems to me that -pi would be about as easy as a test value as one could find. So if we were to plug -pi in for the x in the derivative, which would be this guy right here, I'm going to kind of put a cloud around him so we see where he's at, 1 plus the sine of -pi. The sine of -pi, well, what does the sine of -pi look like? Well, we can envision our sine graph one more time over here. The sine of -pi would be right there. That would be 0. So, of course, we end up with the result of -1. Of course, that sine is negative, so we would be dealing with a graph that is decreasing. Remember your first derivative test. All right. Between -pi/2 and 3pi/2, obviously the easiest test value would be 0. In this case, we would still have -1 on top over 1 plus the sine of 0. The sine of 0 is 0. Once again, we get a -1 result. Negative sign, of course, and the function is still decreasing. No change in its behavior. Well, the last interval here is probably going to be the trickiest one because to come up with values between 3pi/2 and 2pi, you're going to have to be a little clever. And I would perhaps suggest maybe rewriting these two so that they would avail like a denominator of 4. So 3pi/2 would be 6pi/4. 2pi would be the same as 8pi/4. And then it becomes pretty easy to see that, oh, it's 7pi/4. F prime of 7pi/4 happens to be our test value. Well, again, we're going to have -1 on top over 1 plus. Well, the only thing that seems to be sort of hampering us now is our ability to figure out what is the sine of 7pi/4, which can be a little tricky because of the fact that it's outside of our quadrant that we're perhaps most comfortable working with. I want to leave this to you. I know this video is getting a little long as it is, but I want to leave it to you to verify that we would indeed still get a negative result out of this. I think what happens is that the value that you get here is just, it's either positive or just negative enough to keep the entire denominator being a positive value. So we decrease on every interval that this function is defined. Not a very typical result, but it is indeed possible. And the good news about when you have decreasing, decreasing, decreasing is that it makes question 7 very, very easy to answer, because since there's no change in the behavior, this particular problem will have no relative extrema whatsoever. Now that can come back and haunt us later on, because we won't have any nice reference points that we can throw into our sketch. But nonetheless, we'll have to deal with it, and we'll push on with it. Okay, we're getting close to the home stretch. I know these problems are quite long. We're going to remember from our previous screen that the f prime was 1 over, remember, I'm sorry, negative 1 over 1 plus sine of x. And from here, we're going to take another derivative to get into our second derivative analysis. So f double prime would be, once again, I'm going to stick with the, I'm going to go ahead and stick with the chain rule, or the quotient rule. Of course, we could do the chain rule with this particular problem. They're about the same level of difficulty. The derivative of the top would be 0 since it's a constant. Multiply that by the bottom. Subtract the top. Multiply by the derivative of the bottom, which in this case is 0 times the cosine, all divided by 1 plus sine quantity squared. And this will end up simplifying to be simply cosine on top over 1 plus sine squared on bottom. Hopefully you all see that simplification, as all of this stuff here basically will cancel itself to 0. Double negative would make a positive. All right, so we're at the stage where we're interested in finding some critical values that would pertain to our second derivative. So those could perhaps occur, say, when the second derivative is 0. That would be concerning where the numerator is 0, where cosine of x equals 0. Again, this might feel like something that we've done many, many times already, and we have. X, in this case, would equal plus or minus pi over 2 and plus or minus 3 pi over 2. If you recall, we solved this exact same equation earlier when we were finding the, what were we finding? We were finding places where the x-intercepts might occur. Just wanted to take you back. It was actually part 1 right here. So again, I don't feel much need in repeating any work that you've already done, because let's all face it, these problems are long as they are already. So we have these 4 critical numbers. I guess that also means that we should be at least entertaining the possibility critical numbers for the denominator. Well, once again, 1 plus sine of x would equal 0 in this case as well. So when the second derivative is undefined, we can pretty much rely on the fact that it's going to be at this particular stage. And once again, I am not going to redo any work that we've already done before, but negative pi over 2 and 3 pi over 2 turn out to be the results, if you recall, which is nice because we've already got those guys as critical numbers from above. Negative pi over 2 and positive 3 pi over 2. Double check, make sure that I did write the correct ones. Yes, I did. So 4 critical numbers means, how many intervals? How many intervals we're going to have here? Looks like we're going to have 5 intervals. I'm going to go ahead and get rid of this so that I can see my derivative. Put together the lines for the chart. Five intervals. So we have to be a little careful here. There's 1, 2, 3, 4, and 5. And we'll use the first column with our typical interval, test, sign, conclusion. Starting at negative 2 pi, we'll go to negative 3 pi over 2. From negative 3 pi over 2, we're going to go to negative pi over 2, negative pi over 2, to positive pi over 2, positive pi over 2, to 3 pi over 2, and finally 3 pi over 2 up to 2 pi. Now, I'm going to try to save a little bit more time here if possible, because again, the testing here is very, very similar to things that we've already talked about over and over again. In each of these boxes, you're going to test something, you're going to test something in the second derivative. Some value that would lie on the interval given. And you will then just determine what the sign of that result would be. And it's going to boil down to some real basic trigonometry. So I'm going to go ahead and reveal these signs, and you can go back and do this test on your own just to make sure that you're very comfortable in doing so. So we're going to find out that on the first interval from negative 2 pi to negative 3 pi over 2, we are going to have a positive sign, as it turns out. And then from negative 3 pi over 2 to negative pi over 2, you will notice that we would have a negative sign. On the interval negative pi over 2 to pi over 2, well, we can do one of these or so very quickly. If we do test to 0, we would have the cosine of 0 on top, which is 1, over 1 plus the sine of 0 on the bottom, which is 0, of course. Square all that, and you get a positive number. So we're positive there. Continuing from positive pi over 2 to positive 3 pi over 2, we would get negative. You can test pi in there very easily. You can try that one on your own. And then at the end here, we find once again that we're going to be positive from 3 pi over 2 up to 2 pi. So our conclusions then, having to do with concavity, would be going from concave up to concave down, back to concave up, back to concave down, to concave up again. Which means we certainly have the potential to have some points of inflection here. In fact, we could have as many as 4 of them. Well, if we look and we see that, oh yeah, we do change concavity. We are concave up to concave down when the x value is negative 3 pi over 2, we find out that that is certainly okay. We could have an x value of negative 3 pi over 2. That was in our domain if you look back at one of the original analyses that we did in part A. And then I'll leave it to you guys to verify the fact that if you were to plug negative 3 pi over 2 back inside of the original function, you would get 0 for a y value. Negative pi over 2, we changed concavity there, but if you recall, negative pi over 2 was not going to be a point of inflection because it's a position where there's a discontinuity, or more importantly, a position where you have a vertical asymptote from part 5. Let's remember that same thing with 3 pi over 2. So that means then, that means that at the x value of pi over 2, we would have another point of inflection. If you were to plug that back into the original function, once again, I promise you'll get 0 as a result. And then, as we said, 3 pi over 2 cannot show up as a point of inflection since it's a vertical asymptote. Woo! We are ready. We are ready to go back to the original graph here. Hopefully you've got all of the analysis in front of you, because I'll have to switch screens around, and that's not going to be a lot of fun. So follow along with me. I'm going to go ahead and sketch in initially our y-intercept, which we found, I believe, to be 0, 1. And I think we did have a pair of x-intercepts, if you recall, pi over 2 comma 0 and negative 3 pi over 2 comma 0. We remember we had a couple of vertical asymptotes, if you recall. One of them was at negative pi over 2, and the other one is at positive 3 pi over 2. We did not have any points that served as relative extrema, and any points that served as points of inflection are already showing up here as x-intercepts. So really, guys, this is all you got. You now have to put the increasing, decreasing behavior alongside the concavity behavior, adhere to these asymptotes, cross through these 3 points, and then you've got your graph. So if you remember the first interval from negative 2 pi up to negative 3 pi over 2, we were decreasing and also concave up. Well, the best way to give us that sort of feel would be a curve that would look something like this, decreasing and concave up. We want negative 3 pi over 2 for the x value to be a point of inflection. We're going to change to concave down. And remember, the whole graph was decreasing, so that's going to be pretty easy to remember. We're decreasing the whole time. So that does a pretty good job of dealing with the first branch of this. Secondly, we're continuing to be decreasing, but if you recall, I believe we are concave up again, starting at negative pi over 2. We can verify that real quickly by going to the second derivative test. Yep, sure enough, between negative pi over 2 and positive pi over 2, we're going to be concave up, and then we'll switch to down. So if we're concave up, decreasing, we would look something like this. But then at pi over 2, we switch to concave down. I'm going to then make sure I adhere to those vertical asymptotes. And then to finish up, we're going to be decreasing, concave up. Well, once again, the best way to see that is by using the idea of the vertical asymptote. And what you're going to do is you're going to find that you've got yourself sort of this repetitive graph that has this sort of, I don't dare want to call this a cubic function, but it sort of has that negative cubic appearance to it that seems to be replicating itself. And with that, you have sketched the graph of the trigonometric function cosine x all over 1 plus sine of x. As you can see, probably not going to see a problem like this on an assessment, at least in my class, because it does take quite a long time to do. But I love for my students to be able to work on problems such as this, to really, really take care of the 9 items of analysis that you have here. Plus, it does do a good job in brushing up on some of the trig stuff. So anyway, hope you enjoyed, and I'll see you next time. Bye.